All right, welcome back from spring break. Some announcements to share with you here before we get into the content. And I want to share these announcements with at least one person who can't be here in person today. So I'm sharing the announcements on the recording, but I will put timestamps to the different parts of the content in the video so you can jump ahead if you need to. So part of the announcements is just looking at the schedule here for upcoming weeks. So we all got the screen share, look good? All right. So we are coming back from spring break. Today's March 22nd here. So we are at this week. And you can see what we have coming up. We have besides all these text sections, we have a project coming up. Iteration and dynamics is what I call the project here in the syllabus. And that project is going to be due Tuesday, April 6th, probably by 11:59 p.m. Do you have a question? No. No? Okay. I'm going to share the project with you on Thursday of this week, after class, or maybe Wednesday night if I get to it. It is a group project, so ideally you're going to work together. I won't force you to work together, but it would be more ideal if you worked with other people because the concepts are hard enough that you're going to get more out of it if you work with other people. And these are concepts that I might test you on for the project, so you do want to understand it. I made some extra videos to help you through the project. It's not something that we're going to spend a ton of time on in class. So you're going to want to watch these extra videos that I have to help you understand the project. I made them a few years ago. I think I made 5 of them. They're all like, I think between 10 and 20 minutes each to essentially do some examples to help you understand the project. Okay, so again, I'll share that with you either late Wednesday or early Thursday over email or put it on Moodle. And that's something you'll work on. To give you space to help you have time to do the project, there will be fewer homework problems required to turn in for grading, starting on the homework due probably this Friday. As you know, there is a homework due tomorrow morning by 9 that I would like you, if you are able, to bring to my office. I'll send you a reminder tonight. There will also be a homework due at class on Wednesday. And again, if you can't be here or if you can't turn it in person, you will be able to send them to me via email, but ideally you turn them in person on paper. So again, a homework due 9 a.m. tomorrow morning, and then another homework that I will put up here shortly after class, due by class time on Wednesday. But starting with the homework due Friday, it'll be fewer problems, okay? A couple of them here or there still might be long problems, but there will be definitely fewer problems to turn in for grading. I will probably also give you some suggested problems to work on just for practice, and I'll make those odd problems so you can check your answers in the back of the book. But you will not be required to do those. Those will be optional. Starting on Wednesday, we'll also start taking some quizzes that are pretty much, we'll take quizzes most days at the beginning that are about taking derivatives using things like the product rule, the quotient rule, the chain rule, which we will review for a lot of the time today, to help you also pass the gateway exam, which is not on the schedule here on that calendar, but is, I think the date, did I put the date in here or not? Maybe I didn't put the date in here for the gateway exam. I'm forgetting. Okay, it might be in here, it might not be, but these practice quizzes will help you prepare for the gateway. Oh, I did put it here. Okay, excuse me. It's over. I just needed to slide over here. It's planned for April 7th, which is a Wednesday. By the way, Easter is Sunday, April 4th. So there's no class Monday, April 5th. Project's going to be Tuesday night, April 6th. Even though we don't meet that day, you'll turn it in electronically by 11:59 p.m. that night. The gateway exam is April 7th. So these quizzes are meant to help you prepare for the gateway. So again, the gateway exam, you need to pass. It's either pass, fail. It's not given, you're not graded on a point basis. There's 7 questions on the gateway. You have to get 6 out of 7 exactly right. No partial credit. The idea being that you get partial credit for quizzes and exams and homework because we want to give you credit for the effort and for logical work, even if you make small mistakes. But on the gateway, we're also emphasizing that getting things right is important too. Exactly right. It technically is important, okay, in math. So we want to emphasize that. We want to also kind of drill these rules, the product rule, quotient rule, chain rule into your mind so that you learn them better. Okay, that's the motivation. And so study for these quizzes, starting again in class on Wednesday, then on Friday, then next Monday, then next Wednesday. Friday of next week is Good Friday. Monday of the week after is the day after Easter. We also have that day off. Wednesday, you're taking the gateway. You will have enough time in the gateway to double and maybe even triple check your answers. I'll give you more time for the gateway than for the quizzes. But we're practicing. We're trying to practice and give you success in the gateway. Usually, based on people practicing for the gateway, the first time you take it, typically in the past, between 65 and 80% of the class typically passes the first time. If you don't pass, you get more than one chance to take it. You get up to 2 retakes, though they are not the exact same questions. They're equivalent questions, equivalent difficulty, but not exactly the same. So you want to practice. You don't want to fail every single one of them, okay? Shoot for the first one. It's worth the effort. Second exam is the 12th of April. That would be a Monday. And what would that be, 3 weeks from now? And that'll be on a lot, chapters 2 and 3 for sure. Probably also a little bit of chapter 4 on that exam. So that's a lot of content. There's a lot to do. There's a lot to work on here. You don't want to slack off right now. You want to really work hard on getting this stuff, even if you have had calculus before, okay? What are we going to do today in class? A lot of this class, we're going to just practice taking derivatives, okay? So we'll do a bunch of examples. I'll give you time to work on the examples. I still will record the video as we go, but again, I'll put timestamps to when we start the examples and then when we finish them for the video for at least one person who can't join us today. And after we've done a bunch of examples, hopefully at the end, the last 10 minutes or so, we might have time for Mathematica again and talking about parametric curves and motion and that kind of thing. All right, so let's get some practice. So you watch those videos of the lectures 17A and 17B. Hopefully you uploaded that before class today. Today's notes starting now are due still tonight. And in fact, the link is on Moodle. So again, you can do it right after class if you're afraid you're going to forget. But let's get some practice here. Let's review some fundamental facts first. Oh, my video stopped. I don't know why it did that. Fundamental derivative facts. And these are facts you should definitely know for the gateway. Fundamental derivative facts. On taking derivatives, finding derivatives. First property that we talked about back in chapter 2 is the power rule. You know, this is the one you're most used to, the fact that the derivative with respect to x, say, of x to the n power is n times x to the n minus 1. Perhaps the thing that most people remember 50 years after a calculus course is that fact. Okay, but just knowing this fact doesn't mean you know calculus. It doesn't mean you understand it. It's still important to be able to use it, but it doesn't mean you understand calculus. What does the rule say when you've got x to the n power where x is your variable and n is a constant? To take the derivative with respect to the variable, in this case x, take that power, bring it down in front as a multiplier, as a coefficient, do n times x to the n minus 1 power, so subtract 1 from that exponent. So for example, the derivative of x to the 4th power would be 4 times x to the third power. The derivative of something weird like, say, x to the pi power, yes, is pi times x to the pi minus 1 power. When will you ever raise something to the pi power? Hardly ever, except just for a gateway exam on the calculus class, okay? So you should know if you got something like that on the gateway exam, yes, it would be pi times x to the pi minus 1 power. It is technically true. However, it would be very rare in any application. I can't think of any application where you'd actually raise a number to the pi power. But this is still a true fact. Careful. If I wrote something like this, take the derivative of e to the pi power with respect to x, the answer is not pi times e to the pi minus 1 power. It's also not e to the pi. You remember the derivative of e to the x is e to the x. The derivative of this is also not e to the pi. What is it? It's not 1. 0. Why? That's a constant. Yeah, it's a number, exactly. It's just a fancy number, but it's a constant. It's a fixed number. If x is the variable, then the derivative of a constant is always 0. And that does fit with this when you think of n as being 0 power. When n is 0, that's raising x to the 0 power. That effectively is thinking of that as a constant. We've got linearity. The derivative of a sum, f of x plus g of x, is the sum of the derivatives, f prime of x plus g prime of x. And you can also carry constants that are multipliers along for the ride. In its most general form, you can say the derivative with respect to x of some linear combination of functions. Say some constant c1 times a function f1 of x plus some other constant c2 times a function f2 of x, etc. The dots just mean etc. The last term might be cn fn of x. And by the way, when you think about particular examples here, it's very possible there could be some subtractions in there, because when you subtract a number, it's the same as adding -1 times the number. So these constants can be negative, which effectively means you're doing some subtractions. The derivative of that linear combination, linear because these functions are to the first power and you've got just constant coefficients, is the corresponding linear combination of the derivatives. Keep the constants as they are and just take the derivatives of the individual functions and then add all these things up. You've used this plenty of times already. Anytime you take the derivative of a polynomial, you've used this without thinking about it. But it is a fundamental abstract fact to know. And if you need higher math, in particular, if you're an engineering major and you need to take like differential equations or differential equations and linear algebra, or maybe just the linear algebra standalone course, this is an abstract fact you need to know for that course, because it ends up being really useful. This abstract fact is more than useful for just taking derivatives. It helps you solve lots of differential equations for the class that we have called differential equations. And then there's another class called differential equations and linear algebra, which engineering majors typically take with me. Fundamental fact to know. And you do need it for taking, for example, derivatives of polynomials. You use it all the time without hardly thinking about it now. We've done the derivatives of exponential functions. Derivatives of exponential functions. FCNS is my abbreviation for functions. Well, we did the derivative of e to the x. The book talks about the derivative of a to the x, where a is an arbitrary constant. Careful, this is not a power function. Power functions have x in the base, not in the exponent, not in the power. Exponential functions have x in the exponent, the power. That's the variable. A is constant. This is mentioned in the book that even if a is not equal to e, you can still do this, and you get natural log of a times a to the x, not x times a to the x minus 1. That's a bad mistake. Also not a constant, not 0. Technically, we only do this when a is positive and not equal to 1. I mean, you can do it when a is 1, but that's the trivial case, because 1 to the x is always equal to 1. 1 to the x is an exponential function that's just not very interesting. It's the constant function of 1, and so its derivative is always 0. Technically, this does work when a is 1, because natural log of 1 is 0, but we hardly ever use it. We don't think about it that way when a is 1. And yeah, sometimes we give you tricky examples on quizzes or gateway exams where we might say, what's the derivative of something weird like pi to the x? Well, you should still be able to do it. Pi is just a constant. This is an exponential function. The answer is not 0. It's not like this example. There is an x in there. It's just in the exponent. Use this rule. It's going to be natural log of pi times pi to the x. Done. That's all you have to do. In applications, who would ever do such a thing? Probably hardly ever. I can't think of an application where somebody would use this function, but technically this is right, and technically you should know it for the gateway. Can I clarify anything so far here? In lectures 17a and 17b, you saw me talk about the product rule, quotient rule, and chain rule. I also talked about infinitesimals. I did say on Moodle, you didn't have to fully understand the infinitesimal stuff. In fact, hardly anybody does. It's an intuitive approach to things. To fully understand infinitesimals is actually graduate level math. Okay? But that's not the point. The point is just to get a basic intuitive idea about them. And they can be used to intuitively think about derivative meanings and also derive formulas like the product rule, like I did. The product rule says to take the derivative of a product, f of x times g of x, say, but it doesn't matter what I call the functions. I could call it g of x times h of x. I've got a first function, say, here, and a second function, but, you know, multiplication is commutative, so I could actually switch around those roles. Right? F of x times g of x is the same as g of x times f of x. So which one I call the first function and which one I call the second is actually doesn't matter. And the product rule says this gives you, well, one way to write it is to think of it as the derivative of the first function times the second function. And putting these things next to each other without a dot, that is understood to mean multiplication, plus the first function times the derivative of the second function. Did I say that right? That's the derivative of the first function, f prime, times the second function, g of x, plus the first function times the derivative of the second. But hey, addition is also commutative. You don't have to think of it that way. You don't have to go derivative of the first times the second plus the first times the derivative of the second. You could do this one first, the first function times the derivative of the second plus the derivative of the first function times the second. And since multiplication is commutative, you can switch around those as well. I mean, I don't want to overload you with too much information there, but just realize you can think of it either way and still get the same answer. With the quotient rule, you have to be more careful. Quotient rule, the derivative of a quotient, in other words, a fraction or a ratio, where we have a high function, H-I-G-H is how to spell high, and low function, L-O-W, though maybe sometimes you feel like abbreviating those to H-I and just L-O or something. when you divide things, either numbers or functions, the order does matter. You know, 8 divided by 2 is 4, but 2 divided by 8 is 1/4. Not the same thing. So the order of high and low does matter, of course. And also, when you take the derivative, when you get the answer, the order on the top of the fraction also matters. And this is one of the most common mistakes people make on quizzes and the gateway that prevents them from passing the gateway, for example. The top, the way I remember it is to always start low, low. Low d high minus high d low over the square of what's below. Okay, it just makes more rhyming sense to add the b in there for below. Low d high. Low is the g function. D high. D means derivative. D high is the derivative of the high function. Minus high. D low is the derivative of the low over the square of what's below. I could just say square of low, but below just sounds better there. Low d high minus high d low over the square of what's below. I mean, when you're taking the quizzes of the gateway, you can be saying that in your mind. Don't say it out loud. You got to get the order right on top, though. Start with low. Always just remember, you got to start with low. Low d high minus high d low over the square of what's below. Start with low. Okay? One of the most common places people make mistakes on quizzes and gateways. And then we have the chain rule. For the derivative not of a product, but a composition of functions where one function is plugged into the other function. F of g of x. Use all those parentheses and make them approximately the same size that I did. Here, g of x is the quote unquote inside function. Or maybe I should just, okay, maybe I should just point at the g here. F is the outside function. When you compose functions, you work inside out. When you plug a number into this function, f of g of x, you figure out g of x first. Then take that number and plug it into f in place of x in the formula for f. It's not a product. It's not f of x times g of x. It's f of g of x. We could use the circle notation. We could also write this thing here as f circle g of x if we preferred. Fog of x, if you like, just a little flair, naming flair. But the circle there is not an O. It's actually not really a circle in the usual sense either. It's just a symbol representing a way to combine these functions to get a new function, just like a plus sign or a minus sign or a dot for a times or a division symbol. Though function composition is not commutative. G circle f is a different function in general. The chain rule says, take the derivative of the outside function, find f prime, but don't plug x into it, plug g of x into it. And then multiply times g prime of x. That's what the chain rule says. There is a way to write this with the Leibniz notation as well that's commonly done. I think I'm going to not do that right now because it might be confusing. The dy dx notation is what I mean when I say the Leibniz notation. These are the fundamental derivative rules. The abstract ones being rules 1, 2, 4, 5, and 6. 2, 4, 5, and 6 actually. 1 and 3 are more specialized because you're talking about special functions there. But I'm going to go ahead and put them in this list as a fundamental derivative facts anyway. Let me introduce you to a couple new ones. Derivatives of trig functions. assuming, and this is absolutely fundamental, assuming the input variable, if you want to think of it as an angle, is measured in radians, not degrees. Assuming x is in radians. Now, do you have to think of x as an angle? No, you actually don't. But if you do want to relate these functions to angles, then you have to think of x as being measured in radians. So you might as well just say it, pretend it. And when you graph it in your calculator, you got to make sure you're in radian mode. These rules that I'm about to write down do not work if you think of x as an angle in degrees. Think about it. I mean, sine of 1, it doesn't even make sense to think about them as the same function if x is measured in radians versus degrees. Sine of 1, when 1 is in degrees, sine of 1 degree is real close to 0. Sine of 1 radian is not very close to, well, it's a lot further from 0. Try it on the calculator. I'm in radian mode. Let's go to, excuse me, degree mode. Sine of 1 degree is very close to 0. 0.01745. If I now go back and go to radian mode, which should be your default, except when you need to solve physics problems involving triangles, radian mode should be your default. Then sine of 1 is 1 radian, not as close to 1. It's 0.84147. Why? Well, 1 radian, if you convert it to degrees, is like 57 something degrees. It's in degrees, it's 180 divided by pi, actually, about 57.3 degrees. It's a bigger angle. It's got to be a different sign. So it affects the function, and it also affects the derivatives if you're thinking of x as being in radians or degrees. You can figure out the derivative of sine of x if x is in degrees, but there's an extra fudge factor that needs to come into play. So we mostly avoid talking about that. The derivative of sine of x is cosine of x, amazingly, and very fortunately. That's a very fundamental thing to know. And the derivative of cosine of x turns out to be the opposite, negative sine of x. Now, you got to be careful when I say negative sine. Do I mean sine sin or do I mean sine sign? I mean negative sine sin, although there is a negative sine sign there in what I wrote. It's the opposite of the sine function. The negative of the sine function, you might say. Got to be careful with what you mean. Those are the most fundamental facts to know. A couple more you need to know for quizzes in the gateway. The derivative with respect to x of tangent of x is secant squared x. And the derivative of secant of x is secant of x times tangent of x. And you might scratch your head and wonder, what was secant again? Secant of x, by definition, is the reciprocal of cosine of x. 1 divided by cosine of x. That's what secant of x is. Which is not the same as what the inverse cosine function is. Those are not the same. The inverse cosine function, we use a -1 as if it's a -1 power, but it's really not. That's why some people prefer calling it the arc cosine function instead. If we mean cosine of x to the -1 power, in other words, 1 divided by cosine of x, we call it secant of x. Or we write it as a fraction, or we write it with parentheses. We could write this, cosine of x quantity to the -1 power, then you would really mean a -1 power. but that's not the same as the inverse cosine function. These two are the most useful ones in this class, at least. These two you should know, but in this class, we don't find a ton of use for them. Maybe one place where we might use 3 that I can think of. However, these facts 3 and 4 here, oh, I should have probably labeled these with letters, sorry. A, B, C, and D. These facts C and D do end up being a bit more useful in calculus 2, because they help you do some certain integrals that are useful integrals to do, if you know what integrals are. And if you don't, you will eventually know what integrals are here in about a month or so. Actually, I am actually going to talk about integrals today. I forgot about that briefly. Maybe I should even do it right now. Yeah, I do want to talk about integrals. It is on the Moodle list. Not labeled with the word integral, but with the word antiderivative. I guess we are gonna get to the practice here. Just hang on here. Antiderivatives, also known as indefinite integrals. What's an antiderivative? Well, evidently it's the opposite of a derivative somehow. We know the derivative of x squared is 2x, right? If I started with the 2x, I could ask, what's a function whose derivative is 2x? X squared. X squared is an antiderivative of 2x. I just told you the derivative of the sine function is the cosine function. Therefore, an antiderivative of the cosine function is the sine function. Go back the other way. The derivative of the cosine function is the negative of the sine function. Therefore, the antiderivative of the negative of the sine function is the cosine function. It's just taking these facts and going backwards. There's a special notation that is used involving something called the integral sign. It's a very beautiful symbol, looks like this. If I write that symbol, this integral sign, you should know this, you should be taking notes on this, and I write 2x here, and then emphasize that x is the variable by putting a dx here, then I have written an indefinite integral. And when you see something like this, and you should know this for exam 2, to evaluate this, you find an antiderivative. In fact, you don't find just any antiderivative, you find the most general one, x squared plus an arbitrary constant c. This equation is equivalent to the fact, it means the same thing as the fact that the derivative with respect to x of a function x squared plus c, where c is an arbitrary constant, is, well, first by linearity, this is the derivative with respect to x of x squared plus the derivative with respect to x of the constant. But that's 2x plus 0, or just 2x. These two equations, this one here and this one equaling this here, those two equations mean exactly the same thing. They are saying exactly the same thing in different ways. This one is saying the derivative of x squared plus c, where x is your variable, with respect to x, is 2x. This one says the most general antiderivative of 2x with respect to x, emphasizing x is the variable, is x squared plus c, where c is arbitrary. And when you do these indefinite integrals, you always put the plus c there. And in Calc 2, your gateway is about indefinite integration, finding antiderivatives. And when they forget the plus c, they don't get full credit and they fail the gateway, if they forget it in more than one spot at least. You're not going to have a gateway question about this. Your gateway is about derivatives. But you should still know this for the purposes of understanding things I talk about in class, and also I could put this kind of problem on the exams, the regular exams where you can get partial credit. If you forgot the plus c on the exam, I give you some partial credit. I'll give you partial credit, not full credit because you forgot the plus c, but you will get partial credit. Antiderivative of cosine of x with respect to x is what I just said what that was 3 minutes ago, or 4 minutes ago. What was it? Nope, it's positive sine of x plus c. I'm glad you tried anyway, it's okay. We can make mistakes. Because the derivative with respect to x of sine of x plus c, where c is any constant, is cosine of x plus 0, which is cosine of x. The derivative of any function like this is cosine of x, where c is any constant. Therefore, your most general antiderivative, or antiderivative if you prefer, of cosine of x is sine of x plus c. I tend to say antiderivative, but plenty of people say antiderivative. I'm a little lazy, saying antiderivative is a little quicker. These two equations mean the exact same thing. They represent the exact same truth, the exact same fact, just with different symbols thought about in different ways. And it does turn out that the antiderivative of sine of x is the opposite of cosine of x plus c, because the derivative with respect to x of the opposite of cosine of x plus c, well, let's be careful, that's a linear combination. I can bring the negative sign in up in front, is the negative of the derivative of the cosine function plus the derivative of the constant c. The derivative of the cosine function is the opposite of the sine function. The derivative of a constant is 0. Two negative signs cancel to give you the sine function. All right, now let's get some practice with derivatives. So this is a warm-up for the quiz on Wednesday. I wanted to mention this at the beginning, I forgot. Actually, on Wednesday's class, we're not going to take the quiz right away, but I do want you to be here right away. My daughter wants to share an announcement with you. She's going to join our class, even though she's not in the class. She works for ACR Homes, and she's going to share with you a work opportunity if you're interested for the summer, first few minutes of class. And then after that, we'll take the quiz. And then after the quiz, we'll work on other stuff. Can I clarify anything here? You should know these integrals, not for the quizzes or the gateway, but for exam 2, and technically exam 3 in the final exam as well. There are other derivative facts that I haven't mentioned today that you do need to know for the gateway that are not on this list anywhere. In particular, I'm thinking of derivatives of logarithms and derivatives of inverse trig functions like inverse cosine, inverse sine, and inverse tangent. Also again called arc cosine, arc sine, and arc tangent. Those are not anywhere here yet, but we will derive them soon, this week probably, yeah, Wednesday even. The key to deriving them is the chain rule, actually, and the definition of what inverse functions are. But let's get some practice. So I'd like you to take the derivative of what I'm going to show you here. And In this example that you should work on, I'm going to tell you you're going to need more than one rule. And for quizzes and the gateway, you should be able to handle more than one rule in a given problem. I would like you to differentiate e to the negative x times cosine of 2x. And if possible, simplify your answer. Probably best to do it with the product rule instead of the quotient rule, though in theory, you could do this with the quotient rule because when you multiply by e to the negative x, it's the same as dividing by e to the positive x. Pretty important kind of function example. It comes up a lot in differential equations with harmonic oscillators, like a mass and a spring. So why don't you take a couple minutes and see if you can get the answer, then we'll work on this together. You'll definitely need the chain rule, and you can either use the product rule or the quotient rule. Here's a little hint. I'm going to start working through this, but if you want to try to finish it on your own, you don't have to look at what I'm doing here. Keep going. Okay, I'm going to go through it here. So you should focus on what I talk about and do here. When you're first learning this, and even if you're not first learning this, I think it's helpful to write this kind of thing first. I've got a first function, I've got a second function, they're being multiplied. I need the product rule. Here you can see I'm thinking of it as the derivative of the first function times the second function, plus the first function times the derivative of the second. This helps you avoid mistakes. Once you practice enough, you could maybe skip this step and just start taking these derivatives right away. But I think it's especially helpful for this example, because with both of these derivatives, here and here, I actually need the chain rule. Although with this one, you could think of that as 1 divided by e to the x and just use the quotient rule. Let's think about them separately here. A separate line, the derivative of e to the negative x. E to the negative x can be thought of as a composite function, f of g of x. What's the inside function? What gets done first when you plug a number in? You got to negate it, multiply it by -1. Find its opposite. You know, if you plug in -7, then negative of -7 is +7. That's the inner function, the inside function. E to a power is the outside function. After you find -x, you make it the power of e. So I can think of this as f of g of x, where f of x, the outside function, is e to the x, and g of x, the inside function, is -x. So the chain rule says that derivative is f prime of g of x. Take the derivative of the outside function, plug in the inside function, then multiply times the derivative of the inside function. Careful. Okay, I guess I have to look at these and I have to take their derivatives. Yeah, I probably didn't give you enough time if you are new to this kind of thing. What's the derivative of e to the x? Well, it's e to the x. Natural log of e is 1. That natural log of a factor that I showed you 25 minutes ago is 1, because natural log of e is 1, because natural log is base e. That's why e is so special. And I will need g prime as well. G prime of x. G of x is -x, -x to the first power. Bring the negative sign along, bring down the 1 times x to the 0 power. Well, you didn't have to do that. That's just -1. So comparing what I've got here with what I see here, I need to take f prime, which is e to the x, and replace x with g of x, which is -x. So I get e to the -x. But then multiply times the derivative of g, -1. So in the end, I get negative e to the -x for that derivative. Does that make sense? Can I clarify that? If you think about it in the right way, it can be done without going through all this stuff. Here's how I tend to think about it. And I guess I'm recommending you think about it this way too. If this were just, I look at this function and I say, if that were just an x there, then it would be easy. If that were just e to the x, then the answer would be e to the x. Hey, but it's not an e to the x, it's an e to the -x. Well, let me just pretend it's an e to the x first. And start to write down the answer as e to the x, but then say, wait a minute, it's not just an x. Replace x with what it actually is, -x. And then take the derivative of -x and multiply. Now that might sound confusing and like a lot when you first do it. And you're like, how can I do that in my head so quickly? Like I may need to do it quickly. Practice. Let's practice with the other one, the derivative of cosine of 2x. The derivative of cosine of 2x, we still aren't finishing this problem quite yet. Okay, let me practice in the way that I just told you. I look at this and I say, if that were just cosine of x, then the answer would be easy. Negative sine of x, right? The opposite of the sine function. But it's not just an x, it's a 2x. So I need to use the chain rule. But if I initially pretend it's just an x, I start writing the answer as negative sine of x. But then I say, hey, wait a minute, hold on. It's not just an x, it's a 2x. And then don't forget to multiply it by the derivative of 2x, which is 2. Done. That kind of thing is going through my mind as I figure out the answer over the course of about 3 seconds in my mind. I'm serious. Even here, what, 33 years or so after I first learned this stuff? 34 years, something like that. That kind of thing is what goes through my mind. I recognize this is a composite function. Inside function is 2x. Outside function is the cosine function. Why? Because when you evaluate this function, you first multiply by 2 before taking the cosine. Order of operations is essential to understand. If I want to think about it with this stuff, I can. The f of x, the outside function, would be the cosine function. The g of x, the inside function, would be 2x. F prime of x would be negative sine of x. G prime of x would be 2. This thing here is indeed f prime of g of x. And this thing here is indeed g prime of x. If you replace x in the formula for f prime with g, which is 2x, you'll get exactly what you see here, negative sine of 2x. And if you multiply by g prime, that means multiply by 2, because g prime equals 2. When you're first learning this, yes, go ahead and do this stuff, but try working on it the way that I just told you as well. Anyway, coming back to finish the problem here now, use these facts. You're going to get negative e to the negative x there, times cosine of 2x, plus e to the negative x times, what's this answer? It's negative 2 sine 2x. That is the answer. And it's good enough to leave it like this on quizzes and the gateway, though it's possible I might ask you to simplify it on the exam. Question? Yeah, do you hear me do like the times 2 at the end instead of the sine? Like if you did negative sine 2x times 2. Negative sine 2x times 2, put the 2 at the end is what you're saying? That's fine, you can put it at the end. Okay. If you put it in front of the sign, do make sure to for sure put a dot there. You listening? Here's another common place people make mistakes on the gateway and it prevents them from passing. In this case, you have to have this dot here, because if you don't have it there, or at least if you don't have parentheses there, I'm putting both, then it looks like e to the negative x minus 2 sine of 2x. But that's not what we're doing here. We're doing e to the negative x times negative 2 sine 2x. Those are different things. Yes, what you learned about order of operations in what, 5th, 6th grade or something is fundamental to not making mistakes in calculus here in college. Do I need to simplify it? And should you be able to? Yeah, you should be able to. And sometimes it's useful to simplify it for regular exams where you can get partial credit and also homework. And what's actually most useful to do is to factor out any common factors. There is a common factor of e to the negative x that can be factored out in front, and also the minus sign for that matter. Negative e to the negative x can be factored out, and you could therefore write your answer like this. And notice I'm putting a plus sign inside here because I factored out a negative sign there. So there's a plus in both spots now. That's also a correct answer, and it's actually a more useful way to write the answer. Why? Well, think about what we talked about with derivatives before spring break. We're not going to get to the parametric curves. That's okay. It's okay. That's sort of a sidelight at the moment. Think about what we talked about with derivatives before spring break. We talked a lot about how graphing f prime and graphing f double prime and figuring out where they're positive and negative and 0 helps you graph f, or at least helps you understand the graph of f. Where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Where does it have a local max, like a little hilltop? That's where the derivative is 0. Writing it in factored form helps you figure out more easily where this function, this derivative, is positive, negative, and 0. And in this example, because e to the negative x can never equal 0. Never, ever, 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 ever think that e to a power is 0. And by the way, I'm saying that with extra ever, ever, evers because I once made the mistake of saying e to the 0 was 0 on a graduate level exam. I accidentally wrote e to the 0 was 0 in one of my problems. And my professor in grading the exam, well, he was kind of a crazy professor, more crazy even than me. And he talked pretty funny. He talked like this. And he would like get super excited in class and he would start drooling and spitting. And I hope I don't do that, though I guess the shield is helping me here. And when you made mistakes on exams, he would write in big red letters what your mistake was. And he'd sometimes make fun of you. And he made fun of me there. And he wrote, "What? Are you crazy? Were you sleeping?" And yeah, I mean, some students took offense at that kind of thing. I thought it was kind of funny. It was just his personality. And yeah, I must have been sleeping because yeah, e to a power is never, ever, ever, ever 0. Is that really right? Yeah, it is right. There is some engineers think it's incorrect, but I won't get into why. So this is never 0. So the only way this derivative is going to be 0 is if this thing inside the parentheses is 0. So to solve for where this equals 0, you'd set this part equal to 0. You'd ignore that part, even though it is part of the derivative. And setting that equal to 0 and solving for x, would that be easy or hard? It could be done, I think. You'd probably end up needing to rearrange the equation and rewriting it in terms of tangent and taking the inverse tangent. I think it could be done, but that is something very useful. So yeah, on quizzes and gateways, that's fine. But in exams and homework, you should be able to do this, and you should be able to use something like this. Here. By the way, getting back to indefinite integrals, this fact that we just derived would mean that the indefinite integral, I'll go ahead and write it in the factored form, of negative e to the negative x times in parentheses cosine of 2x plus 2 sine of 2x would equal the original function here, plus c, e to the negative x cosine of 2x plus c. But wait a minute. How in the world would you ever know that unless you did the problem to begin with? Yeah, it would be difficult to know unless I did the derivative problem to begin with. Though there are ways to figure it out, even if you don't do the derivative problem. In the big scheme of things, indefinite integrals are actually more useful than derivatives and definite integrals. I haven't said what a definite integral is yet. If there's an indefinite integral, there must be a definite integral. Integrals are, generally speaking, more useful than derivatives. Calc 2 is in general more useful than Calc 1, but derivatives are still plenty useful as well. Take a breath. Let's do one more example, and I guess we'll work on it together here because we're short on time. Find the derivative with respect to x. Let's make one where we have to use the quotient rule. Well, actually, you can always avoid the quotient rule, but it's probably better to use the quotient rule. Let's make the function e to the x squared divided by x cubed plus 1. Let's take the derivative of that function. You actually always can avoid the quotient rule because you can think of f of x divided by g of x as f of x times g of x to the negative 1 power. And then you can use the product rule instead, along with the chain rule when you differentiate the second function, where the negative 1 power is your outside function. That makes sense? I mean, you don't need to know it for the next homework assignment, but it's worth noting for the future, and I probably will mention it again later this week. So you can always avoid the quotient rule. There are times where you cannot avoid the product rule, the chain rule. And this is, well, here we will use the quotient rule. So remember, it's low, start with the low d high minus high d low over the square of what's below. Low is that, use parentheses. Parentheses must be there, must. Low d high, I'll write the derivative of the high with the ddx notation, meaning I haven't taken the derivative yet, but I know I need to. Low d high minus high d low means the derivative of the low function. X cubed plus 1 over the square of what's below, x cubed plus 1 quantity squared. All those parentheses that you see there must be there when you write this. It's wrong if they're not, because it represents the wrong answer and it'll lead you to the wrong simplified answer as well, and it would lead you to bad graphs and that kind of thing. That derivative is fairly easy. That's 3x squared plus 0, or just 3x squared. This derivative is not quite so easy. What rule do you think we need for that derivative? This one right there. We will need the derivative of e to the x, that's true, but we'll need another more abstract rule. Product rule, quotient rule, or chain rule, which one? Chain rule, because there's an inner function, x squared, the squaring function gets done first, and there's an outer function, e to the x. Let me go ahead and just think about it without writing down the f and the g. Listen real carefully. Okay. By the way, e to the x squared really means, when you write this, it really means this. It does not mean this. Those are different things. Because if you meant that, you'd either write that or you'd write this. And these are different functions. These two things are not equal. Not equal. So you implicitly mean do x squared first, then raise e to that power. You do not mean this, where you would be raising e to the x power first and then squaring, which is equivalent to that by property of exponents. So low d high, derivative of this, chain rule. Okay, pretend, I look at this, I say, if that were just an e to the x, it'd be easy. It would just be e to the x would be the derivative. But it's not, it's e to the x squared, so I need the chain rule. I start taking the derivative as if it's an x. I start writing e to the x, but then I say, pause and say, hey, it's not just an x, it's an x squared. Now multiply times the derivative of x squared. Done. That's how to get good at doing the chain rule fast in your head, is to think the way that I think, or some slight modification of the way I think. I see it's a composition. I know I need the chain rule. And I say, if it were just an e to the x, it would be simple. The answer would be e to the x. But it's not. I start writing e to the x, but then I remember it's e to the x squared, so I need to replace x with x squared. Then multiply times the derivative of x squared with respect to x, which is 2x. Low d high minus high d low over the square of what's below. Can this be simplified? Yeah. Is it worth simplifying it much? This is fine for the answer on the quizzes or the gateway. But for purposes of a homework or exams where you might need to like graph this function or something, or find its local max or min points, or its concavity being concave up or concave down, etc. We need the second derivative for that, and that would be a real big mess. It would be good to factor out any common factor out of the numerator. There is a common factor of e to the x squared. That's good. That can be factored out. There's also a common factor of one factor of x. So I could factor out x e to the x squared out of the top. And when I do so, what am I left with? I'm left with an x cubed plus 1 for one thing, and also a times 2 here. And then minus 3x. Sometimes when you do this, You can simplify even more, maybe by canceling this with maybe one of these factors. That happens sometimes. You can also simplify this by distributing the 2 through the parentheses here. And if you do so, you'll get 2x cubed. Then I'll write the minus 3x plus 2. And therefore, if you were trying to figure out where this derivative is 0, you'd figure out, well, one place it's 0 is when x is 0 because you have the factor x right there. And other places it's 0 is where this is 0, which would include at least one real number. There's at least one real value where this is 0. There could be one or two more. But that's not a guarantee. You have to graph it to see. Okay. Really, really fundamental stuff here. Make sure you practice a lot. Like I said, there's a homework due at 9 a.m. tomorrow, and I'll quickly get the homework due at class time on Wednesday up soon. Don't forget about the getting the participation notes up as well.